So now we're going to continue our discussion of derivatives, and we're going to now talk about applications of derivatives. And so there were lots of applications of derivatives that we looked at. I'm going to highlight some of them right now. So we talked about related rates. We talked about optimization problems. We talked about increasing and decreasing, and we talked about concave up and concave down. So those are just a few of the applications. Let's look at some examples related to these. So let's say all edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the volume changing when each edge is 2 centimeters? So the first thing in this case, because we're working with a physical object, a cube, we probably want to start by making a sketch of what's going on. So here I'm going to do my best to draw a cube for you. Probably won't be the greatest thing you've ever seen before, but yep, I'll try. That's my shoddy attempt at making a cube. But anyways, what's nice about working with a cube is that each side has the same length. So I'm going to give it one variable name. I'll call it x. So we want to identify a couple of things. This is a related rates problem, so we want to start by talking about the equation involved here. If I look back through my problem, I'm talking about the volume of a cube. So that's the formula we're going to work with. Volume is length times width times height. But remember, every side is x. So length, width, and height, they're all x. So the volume will be x cubed. What are our known values? So in particular, we know this rate of change here of the edges or the sides. So that tells us dx dt is 6 centimeters per second. And what is it asking us to find? Find how fast the volume's changing. So find dv dt when x is 2 centimeters. So you're going to take your equation, v equals x cubed, and you're going to take the derivative of both sides using the chain rule. So dv dt will be 3x squared dx dt. And then we're going to plug in the things that we know. So in particular, I know x here, and I know dx dt. And that's going to allow me to solve for dv dt. So dv dt will be 3 times 2 squared times 6. 12 times 6, or 72. And you always want to put units on here. So this is 72. So we were working in centimeters, and because we have volume here, it's going to be cubic centimeters. And our unit for time, if we look back, our unit for time was seconds. Cubic centimeters per second. And there's our how fast the volume's changing. All right, let's look at an optimization problem now. So look at the following example. Find the length and width of a rectangle that has a perimeter of 80 meters and a maximum area. So with optimizations, you always have a constraint. So here, let's draw our rectangle. So one side length will be the length and another side length will be the width. And so our constraint here comes from this perimeter is 80 meters. So if I add up all four sides, well, this side is also the length and this side is also the width. So our constraint is 2 times the length plus 2 times the width is 80. And then we're trying to maximize area, and the area of a rectangle is length times width. So what you're going to do is take your constraint equation, and I'm going to solve for one of my variables. First thing I'm going to do is take my equation and divide by 2, everything by 2, so I will get length plus width equals 40. And if I solve for length, it doesn't matter which one you solve for, I get 40 minus w, and you're going to plug this in to the function you're trying to maximize. So area will then be length times width, which will now be 40 minus w times w, and I'm going to go ahead and distribute. So now you want to take the derivative. A prime will be 40 minus 2w, and you want to set that equal to 0 and solve. W equals 20. And then length would be 40 minus w, 40 minus 20, which would be 20. Now you need to verify that this actually corresponds to a maximum in terms of your area. So if you look at your derivative, you can make your sign chart. Here's 20. Pick something smaller than 20. If you put 10 into your derivative, you'll see that it'll be positive. If you put in 30, if I put in 10 into my derivative, it'll be positive, but if I put in 30, it'll be negative. So my function was increasing, but then switched to decreasing, which means that this right here, this 20, this is a maximum. So you've verified that this does maximize your area. So the width should be 20 and the length should be 20. So actually, the rectangle should be a square.